physics, from ancient Greek, physis. Nature is a branch of science that developed out of philosophy, and was thus referred to as natural philosophy, until the late 19th century, a term describing a field of study concerned with the workings of nature. Currently, physics is traditionally defined as the study of matter, energy, and the relation between them. Physics is, in some senses, the oldest and most basic pure science. Its discoveries find applications throughout the natural sciences, since matter and energy are the basic constituents of the natural world. The other sciences are generally more limited in their scope, and may be considered branches that have split off from physics to become sciences in their own right. Physics today may be divided loosely into classical physics and modern physics. Elements of what became physics were drawn primarily from the fields of astronomy, optics, and mechanics, which were methodologically united through the study of geometry. These mathematical disciplines began in antiquity with the Babylonians and with Hellenistic writers such as Archimedes and Ptolemy. Meanwhile, philosophy, including what was called physics, focused on explanatory, rather than descriptive, schemes, largely developed around the Aristotelian idea of the four types of causes. Ancient Greece. The move towards a rational understanding of nature began at least since the Archaic period in Greece, 650–480 BCE, with the pre-Socratic philosophers. The philosopher Thales of Miletus, 7th and 6th centuries BCE, dubbed the father of science, for refusing to accept various supernatural, religious, or mythological explanations for natural phenomena, proclaimed that every event had a natural cause. Thales also made advancements in 580 BCE by suggesting that water is the basic element, experimenting with magnets and attraction to rubbed amber, and formulating the first cosmologies. Anaximander, famous for his proto-evolutionary theory, disputed the ideas of Thales, and proposed that rather than water, a substance called apeiron was the building block of all matter. Heraclitus, around 500 BCE, proposed that the only basic law governing the universe was the principle of change, and that nothing remains in the same state indefinitely. This observation made him one of the first scholars in ancient physics to address the role of time in the universe, one of the most important concepts even in the modern history of physics. The early physicist Leucippus, first half of 5th century BCE, adamantly opposed the idea of direct divine intervention in the universe, instead proposing that natural phenomena had a natural cause. Leucippus and his student, Democritus, were the first to develop the theory of atomism, the idea that everything is composed entirely of various imperishable, indivisible elements called atoms. Aristotle, 384–322 BCE. During the classical period in Greece, 6th, 5th, and 4th centuries BCE, and in Hellenistic times, natural philosophy slowly developed into an exciting and contentious field of study. Aristotle, Greek, Aristoteles, 384. 322 BCE, a student of Plato, promoted the concept that observation of physical phenomena could ultimately lead to the discovery of the natural laws governing them. Aristotle's writings cover physics, metaphysics, poetry, theater, music, logic, rhetoric, linguistics, politics, government, ethics, biology, and zoology. He wrote the first work which refers to that line of study as physics. In the 4th century BC, Aristotle founded the system known as Aristotelian Physics. He attempted to explain ideas such as motion and gravity with the theory of four elements. Aristotle believed that all matter was made up of ether, or some combination of four elements: earth, water, air, and fire. According to Aristotle, these four terrestrial elements are capable of intertransformation and move toward their natural place. So a stone falls downward toward the center of the cosmos, but flames rise upward toward the circumference. Eventually, Aristotelian physics became enormously popular for many centuries in Europe, informing the scientific and scholastic developments of the Middle Ages. It remained the mainstream scientific paradigm in Europe until the time of Galileo Galilei and Isaac Newton. Early in classical Greece, that the Earth is a sphere, round, was generally known by all, and around 240 BCE, Eratosthenes, 276–194 BCE, accurately estimated its circumference. In contrast to Aristotle's geocentric views, Aristarchus of Samos, Greek, c. 310–c. 230 BCE, presented an explicit argument for a heliocentric model of the solar system, placing the Sun, not the Earth, at the center. Seleucus of Seleucia, a follower of the heliocentric theory of Aristarchus, stated that the Earth rotated around its own axis, which in turn revolved around the Sun. Though the arguments he used were lost, Plutarch stated that Seleucus was the first to prove the heliocentric system through reasoning. Greek mathematician Archimedes, famous for his ideas regarding fluid mechanics and buoyancy. In the 3rd century BCE, the Greek mathematician Archimedes of Syracuse, Greek, 287–212 BCE, generally considered to be the greatest mathematician of antiquity, and one of the greatest of all time, laid the foundations of hydrostatics, statics, and calculated the underlying mathematics of the lever. A leading scientist of classical antiquity, Archimedes also developed elaborate systems of pulleys to move large objects with a minimum of effort. The Archimedes screw underpins modern hydroengineering, and his machines of war helped to hold back the armies of Rome in the First Punic War. Archimedes even tore apart the arguments of Aristotle and his metaphysics, pointing out that it was impossible to separate mathematics and nature, and proved it by converting mathematical theories into practical inventions. Furthermore, in his work on floating bodies, around 250 BCE, Archimedes developed the law of buoyancy, also known as Archimedes' principle. In mathematics, Archimedes used a method of exhaustion to calculate the area under the arc of a parabola with the summation of an infinite series, and gave a remarkably accurate approximation of pi. He also defined the spiral bearing his name, formulae for the volumes of surfaces of revolution, and an ingenious system for expressing very large numbers. He also developed the principles of equilibrium states and centers of gravity, ideas that would influence the Islamic scholars Galileo and Newton. Hipparchus, 190–120 BCE, focusing on astronomy and mathematics, used sophisticated geometrical techniques to map the motion of the stars and planets, even predicting the times that solar eclipse would happen. In addition, he added calculations of the distance of the Sun and Moon from the Earth, based upon his improvements to the observational instruments used at that time. Another of the most famous of the early physicists was Ptolemy, 90–168 CE, one of the leading minds during the time of the Roman Empire. Ptolemy was the author of several scientific treatises, at least 3 of which were of continuing importance to later Islamic and European science. The first is the Astronomical Treatise, now known as the Almagest, in Greek, the Great Treatise, originally Mathematical Treatise. The second is the Geography, which is a thorough discussion of the geographic knowledge of the Greco-Roman world. Much of the accumulated knowledge of the ancient world was lost. Even of the works of the better-known thinkers, few fragments survived. Although he wrote at least 14 books, almost nothing of Hipparchus' direct work survived. Of the 150 reputed Aristotelian works, only 30 exist, and some of those are little more than lecture notes. India and China. The Hindu-Arabic numeral system. The inscriptions on the edicts of Ashoka, 3rd century BCE, display this number system being used by the imperial Mauryas. Important physical and mathematical traditions also existed in ancient Chinese and Indian sciences. In Indian philosophy, Canada was the first to systematically develop a theory of atomism around 200 BCE, though some authors have allotted him an earlier era in the 6th century BCE. It was further elaborated by the Buddhist atomist Dharmakirti and Ingye during the 1st millennium CE. Prakutikakyana, a 6th century BCE Indian philosopher and contemporary of Gautama Buddha, had also propounded ideas about the atomic constitution of the material world. These philosophers believed that other elements, except ether, were physically palpable, and hence comprise minuscule particles of matter. The last minuscule particle of matter that could not be subdivided further was termed Parmanu. These philosophers considered the atom to be indestructible and hence eternal. The Buddhists thought atoms to be minute objects unable to be seen to the naked eye, that come into being and vanish in an instant. The Vaisheshika school of philosophers believed that an atom was a mere point in space. Indian theories about the atom are greatly abstract and enmeshed in philosophy, as they were based on logic, and not on personal experience or experimentation. In Indian astronomy, Aryabhata's Aryabhataya, 499 CE, proposed the Earth's rotation, while Nilakantha Somayagi, 1444-1544, of the Kerala School of Astronomy and Mathematics proposed a semi-heliocentric model resembling the Tychonic system, a star map with a cylindrical projection. Susong star maps represent the oldest existent ones in printed form. The study of magnetism in ancient China dates back to the 4th century BCE. In the Book of the Devil Valley Master, a main contributor to this field was Shinkuo, 1031-1095, a polymath scientist and statesman, who was the first to describe the magnetic needle compass used for navigation, as well as discovering the concept of true north. In optics, Shinkuo independently developed a camera obscura. Muslim scientists Ibn al-Haytham, al-Azan, 965-1039, Basra. Physics in Medieval Islam, Science in the Medieval Islamic World and List of Muslim scientists. During the period of time known as the Dark Ages, 5th to 15th centuries, much scientific progress occurred in the Muslim world. The scientific research of the Islamic scientists is often overlooked due to the conflict of the Crusades, and it's possible, too, that many scholars in the Renaissance later downplayed or even disguised their connection to the Middle East, for both political and religious reasons. The Islamic Abbasid caliphs gathered many classic works of antiquity and had them translated into Arabic within the House of Wisdom in Baghdad, Iraq. Islamic philosophers such as Al-Kindi, Al-Kindis, Al-Farabi, Al-Farabius, and Averroes, Ibn Rushd, reinterpreted Greek thought in the context of their religion. Ibn Sina, 981-1037, known by the Latin name Avicenna, was a medical researcher from Bukhara, Uzbekistan, responsible for important contributions to the disciplines of physics, optics, philosophy, and medicine. He is most famous for writing the Canon of Medicine, a text used to teach student doctors in Europe, until the 1600s. The Abbasid Caliphate had its height in 830 CE. Important contributions were made by Ibn al-Haytham, 965-1040, a mathematician from Basra, Iraq, considered one of the founders of modern optics. Ptolemy and Aristotle theorized that light either shone from the eye to illuminate objects, or that light emanated from objects themselves, whereas al-Haytham, known by the Latin name al-Azan, suggested that light travels to the eye in rays from different points on an object. The works of Ibn al-Haytham and Ab. Raynbn eventually passed on to Western Europe, where they were studied by scholars such as Roger Bacon and Watello. Omar Khayyam, 1048-1131, a Persian scientist, calculated the length of a solar year to 10 decimal places, and was only out by a fraction of a second, when compared to our modern-day calculations. He used this to compose a calendar considered more accurate than the Gregorian calendar that came along 500 years later. He is classified as one of the world's first great science communicators. He is said to have convinced a Sufi theologist that the world turns on an axis. Muhammad ibn Jabir al-Arrn. Al-Batten, 858-929, from Harran, Turkey, further developed trigonometry, first conceptualized in ancient Greece as an independent branch of mathematics, developing relationships such as tan equals sin/cos. His driving force was to obtain the ability to locate Mecca from any given geographical point, aiding in Muslim rituals such as burial and prayer, which require participants to face the holy city, as well as making the pilgrimage to Mecca, known as the Hajj. A page from Al-Khwrizm's Algebra. Furthermore, Nasir al-Din al-Tusi, 1201-1274, an astronomer and mathematician from Baghdad, authored the Treasury of Astronomy, a remarkably accurate table of planetary movements that reformed the existing planetary model of Roman astronomer Ptolemy by describing a uniform circular motion of all planets in their orbits. This work led to the later discovery, by one of his students, that planets actually have an elliptical orbit. Copernicus later drew heavily on the work of al-Din al-Tusi and his students, but without acknowledgement. The gradual chipping away of the Ptolemaic system paved the way for the revolutionary idea that the Earth actually orbited the Sun, heliocentrism. Jaber ibn Hayyan, 721-815, was a chemist and alchemist from Iran who, in his quest to make gold from other metals, discovered strong acids such as sulfuric, hydrochloric and nitric acids. He was the also first person to identify the only substance that can dissolve gold: aqua regis, royal water, a volatile mix of hydrochloric and nitric acid. It is disputed whether Jaber was the first to use or describe distillation, but he was definitely the first to perform it in the lab using alembic, from alembic. The most famous Persian mathematician is considered to be Muhammad ibn Mslkhwrizm, 780-850, who produced a comprehensive guide to the numbering system developed from the Brahmi system in India, using only 10 digits, 09, the so-called Arabic numerals. Al-Khwarizmi also used the word algebra, al-jabr, to describe the mathematical operations he introduced, such as balancing equations, which helped in several problems. Medieval Europe. Awareness of ancient works re-entered the West through translations from Arabic to Latin. The reintroduction, combined with Judeo-Islamic theological commentaries, has a great influence on medieval philosophers such as Thomas Aquinas. Scholastic European scholars who sought to reconcile the philosophy of the ancient classical philosophers with Christian theology proclaimed Aristotle the greatest thinker of the ancient world. In cases where they didn't directly contradict the Bible, Aristotelian physics became the foundation for the physical explanations of the European churches. Based on Aristotelian physics, scholastic physics described things as moving according to their essential nature. Celestial objects were described as moving in circles because perfect circular motion was considered an innate property of objects that existed in the uncorrupted realm of the celestial spheres. The theory of impetus, the ancestor to the concepts of inertia and momentum, was developed along similar lines by medieval philosophers such as John Philoponus and Jean Buridan. Motions below the lunar sphere were seen as imperfect, and thus could not be expected to exhibit consistent motion. More idealized motion in the sublunary realm could only be achieved through artifice, and prior to the 17th century, many did not view artificial experiments as a valid means of learning about the natural world. Physical explanations in the sublunary realm revolved around tendencies. Stones contained the element earth, and earthy objects tended to move in a straight line toward the center of the earth and the universe in the Aristotelian geocentric view, unless otherwise prevented from doing so. This section needs additional citations for verification. Please help improve this article by adding citations to reliable sources. Unsourced material may be challenged and removed. June 2013. Scientific Revolution. During the 16th and 17th centuries, a large advancement of scientific progress known as the Scientific Revolution took place in Europe. Dissatisfaction with older philosophical approaches had begun earlier and had produced other changes in society, such as the Protestant Reformation, but the revolution in science began when natural philosophers began to mount a sustained attack on the scholastic philosophical program and supposed that mathematical descriptive schemes adopted from such fields as mechanics and astronomy could actually yield universally valid characterizations of motion and other concepts. Nicholas Copernicus. Polish astronomer Nicholas Copernicus, remembered for his development of the heliocentric model of the solar system. Nicholas Copernicus, Tycho Brahe, and Johannes Kepler. A great breakthrough in astronomy was made by Polish astronomer Nicolaus Copernicus, 1473–1543, who proposed in 1543 the heliocentric model of the solar system. This theory stated the Earth orbits around the Sun, with other bodies in Earth's galaxy, a large group of stars, and other bodies. This heliocentric theory contradicted the ideas of Greek-Egyptian astronomer Ptolemy, 2nd century CE, who stated that the Earth is the center of the universe. The Ptolemaic system had been accepted for more than 1,400 years. In 270 BCE, the Greek astronomer Aristarchus of Samos, c. 310–c. 230 BCE, had suggested that the Earth revolves around the Sun, but Copernicus's concept was the first to be accepted as a valid scientific possibility. Copernicus's book, De Revolutionibus Orbium Celestium, on the revolutions of the celestial spheres, published just before his death, in 1543, is often regarded as the starting point of modern astronomy, and the defining epiphany that began the scientific revolution. Having made the assumption that the Sun was at the center of the universe, Copernicus realized that calculating tables of planetary motion, mathematical charts that described the movements of planets, was much easier and more accurate. Copernicus's new perspective, along with the accurate observations of Tycho Brahe, was used by German astronomer Johannes Kepler, 1571–1630, to formulate laws regarding planetary motions that are still accepted today. Among Kepler's laws is the idea that planetary orbits are elliptical rather than perfect circles. Galileo Galilei, 1564–1642. The Italian mathematician, astronomer, and physicist Galileo Galilei, 1564–1642, was the central figure in the scientific revolution, and famous for his support for Copernicanism, his astronomical discoveries, empirical experiments, and his improvement of the telescope. As a mathematician, Galileo's role in the university culture of his era was subordinated to the three major topics of study: law, medicine, and theology, which was closely allied to philosophy. Galileo, however, felt that the descriptive content of the technical disciplines warranted philosophical interest, particularly because mathematical analysis of astronomical observations, notably the radical analysis offered by astronomer Nicholas Copernicus concerning the relative motions of the Sun, Earth, Moon, and planets, indicated that philosophers' statements about the nature of the universe could be shown to be in error. Galileo also performed mechanical experiments, and insisted that motion itself, regardless of whether that motion was natural or artificial, had universally consistent characteristics that could be described mathematically. Galileo's early studies at the University of Pisa were in medicine, but he was soon drawn to mathematics and physics. At the age of 19, in the Cathedral of Pisa, he timed the oscillations of a swinging lamp by means of his pulse beats, and found the time for each swing to be the same, no matter what the amplitude of the oscillation, thus discovering the isochronal nature of the pendulum, which he verified by experiment. Galileo soon became known through his invention of a hydrostatic balance and his treatise on the center of gravity of solid bodies. While teaching 1589–92, at the University of Pisa, he initiated his experiments concerning the laws of bodies in motion, which brought results so contradictory to the accepted teachings of Aristotle that strong antagonism was aroused. He found that bodies do not fall with velocities proportional to their weights. The famous story in which Galileo is said to have dropped weights from the Leaning Tower of Pisa is apocryphal, but he did find that the path of a projectile is a parabola, and he is credited with conclusions foreshadowing Newton's laws of motion, such as discovering the property of inertia. One of these is now known as Galilean Relativity, essentially the first precisely formulated statement about properties of the space-time beyond geometry of the three-dimensional space. Montage of Jupiter's 4 Galilean moons, in a composite image comparing their sizes, and the size of Jupiter. From top to bottom: Io, Europa, Ganymede, Callisto. Galileo has been called the father of modern observational astronomy, the father of modern physics, the father of science, and the father of modern science. Stephen Hawking says, Galileo, perhaps more than any other single person, was responsible for the birth of modern science. Galileo's support of the Earth revolving around the Sun was controversial, as most people believed in the geocentric model, or the Tychonic system. He was tried by the Inquisition, found vehemently suspect of heresy, forced to recant, and spent the rest of his life under house arrest. The contributions that Galileo made to observational astronomy include the telescopic confirmation of the phases of Venus, the 1609 discovery of the 4 largest satellites of Jupiter, named the Galilean moons in his honor, and the observation and analysis of sunspots. Galileo also worked in applied science and technology, inventing an improved military compass and other instruments. Galileo used his telescopic discovery of the moons of Jupiter, as published in his Sidereus Nuncius in 1610, to procure a position in the Medici court, with the dual title of mathematician and philosopher. As a court philosopher, he was expected to engage in debates with philosophers in the Aristotelian tradition, and received a large audience for his own publications, such as the Essayer and Discourses and Mathematical Demonstrations Concerning 2 New Sciences, which was published abroad after he was placed under house arrest for his publication of Dialogue Concerning the 2 Chief World Systems in 1632. Galileo's interest in the mechanical experimentation and mathematical description in motion established a new natural philosophical tradition focused on experimentation. This tradition, combining with a non-mathematical emphasis on the collection of experimental histories by philosophical reformists such as William Gilbert and Francis Bacon, drew a significant following. In the years leading up to and following Galileo's death, including Evangelista Torricelli and the participants in the Accademia del Cimento in Italy, Marin Mersenne and Blaise Pascal in France, Christian Huygens in the Netherlands, and Robert Hooke and Robert Boyle in England. René Descartes, 1596–1650. The French philosopher René Descartes, 1596–1650, was well connected to and influential within the experimental philosophy networks of the day. Descartes had a more ambitious agenda, however, which was geared toward replacing the scholastic philosophical tradition altogether. Questioning the reality interpreted through the senses, Descartes sought to re-establish philosophical explanatory schemes by reducing all perceived phenomena to being attributable to the motion of an invisible sea of corpuscles. Notably, he reserved human thought and God from his scheme, holding these to be separate from the physical universe. In proposing this philosophical framework, Descartes supposed that different kinds of motion, such as that of planets versus that of terrestrial objects, were not fundamentally different, but were merely different manifestations of an endless chain of corpuscular motions obeying universal principles. Particularly influential were his explanations for circular astronomical motions in terms of the vortex motion of corpuscles in space. Descartes argued, in accord with the beliefs, if not the methods, of the scholastics, that a vacuum could not exist, and his explanation of gravity in terms of corpuscles pushing objects downward. Descartes, like Galileo, was convinced of the importance of mathematical explanation, and he and his followers were key figures in the development of mathematics and geometry in the 17th century. Cartesian mathematical descriptions of motion held that all mathematical formulations had to be justifiable in terms of direct physical action, a position held by Huygens and the German philosopher Gottfried Leibniz, who, while following in the Cartesian tradition, developed his own philosophical alternative to scholasticism, which he outlined in his 1714 work, The Monadology. Descartes has been dubbed the father of modern philosophy, and much subsequent Western philosophy is a response to his writings, which are studied closely to this day. In particular, his Meditations on First Philosophy continues to be a standard text at most university philosophy departments. Descartes' influence in mathematics is equally apparent, the Cartesian coordinate system allowing algebraic equations to be expressed as geometric shapes in a two-dimensional coordinate system was named after him. He is credited as the father of analytical geometry, the bridge between algebra and geometry, important to the discovery of calculus and analysis. Sir Isaac Newton. Sir Isaac Newton, 1642–1727. The late 17th and early 18th centuries saw the achievements of the greatest figure of the scientific revolution, Cambridge University physicist and mathematician Sir Isaac Newton, 1642–1727, considered by many to be the greatest and most influential scientist who ever lived. Newton, a Fellow of the Royal Society of England, combined his own discoveries in mechanics and astronomy to earlier ones to create a single system for describing the workings of the universe. Newton formulated 3 laws of motion and the law of universal gravitation, the latter of which could be used to explain the behavior not only of falling bodies on the Earth but also planets and other celestial bodies in the heavens. To arrive at his results, Newton invented one form of an entirely new branch of mathematics, calculus, also invented independently by Gottfried Leibniz, which was to become an essential tool in much of the later development in most branches of physics. Newton's findings were set forth in his Philosophiae Naturalis Principia Mathematica, Mathematical Principles of Natural Philosophy, the publication of which in 1687 marked the beginning of the modern period of mechanics and astronomy. Newton was able to refute the Cartesian mechanical tradition that all motions should be explained with respect to the immediate force exerted by corpuscles. Using his 3 laws of motion and law of universal gravitation, Newton removed the idea that objects followed paths determined by natural shapes, and instead demonstrated that not only regularly observed paths, but all the future motions of any body could be deduced mathematically based on knowledge of their existing motion, their mass, and the forces acting upon them. However, observed celestial motions did not precisely conform to a Newtonian treatment, and Newton, who was also deeply interested in theology, imagined that God intervened to ensure the continued stability of the solar system. Gottfried Leibniz, 1646–1716. Newton's principles, but not his mathematical treatments, proved controversial with continental philosophers who found his lack of metaphysical explanation for movement and gravitation philosophically unacceptable. Beginning around 1700, a bitter rift opened between the continental and British philosophical traditions, which were stoked by heated, ongoing, and viciously personal disputes between the followers of Newton and Leibniz concerning priority over the analytical techniques of calculus, which each had developed independently. Initially, the Cartesian and Leibnizian traditions prevailed on the continent, leading to the dominance of the Leibnizian calculus notation everywhere except Britain. Newton himself remained privately disturbed at the lack of a philosophical understanding of gravitation, while insisting in his writings that none was necessary to infer its reality. As the 18th century progressed, continental natural philosophers increasingly accepted the Newtonians' willingness to forego ontological metaphysical explanations for mathematically described motions. Newton built the first functioning reflecting telescope and developed a theory of color, published in his work Optics, based on the observation that a prism decomposes white light into the many colors that form the visible spectrum. While Newton explained light as being composed of tiny particles, a rival theory of light which explained its behavior in terms of waves was presented in 1690 by Christian Huygens. However, the belief in the mechanistic philosophy together with the great weight of Newton's reputation was such that the wave theory gained relatively little support until the 19th century. Isaac Newton also formulated an empirical law of cooling and studied the speed of sound. He also demonstrated the generalized binomial theorem, developed Newton's method for approximating the roots of a function, and contributed to the study of power series. Newton's work on infinite series was inspired by Simon Stevens' decimals. Most importantly, Newton showed that the motions of objects on Earth and of celestial bodies are governed by the same set of natural laws, which were neither capricious nor malevolent. By demonstrating the consistency between Kepler's laws of planetary motion and his own theory of gravitation, Newton also removed the last doubts about heliocentrism. By bringing together all the ideas set forth during the scientific revolution, Newton effectively established the foundation for modern society in mathematics and science. Other achievements. Other branches of physics also received attention during the period of the scientific revolution. Wilbert Gilbert, court physician to Queen Elizabeth I, published an important work on magnetism in 1600, describing how the Earth itself behaves like a giant magnet. Robert Boyle, 1627-91, studied the behavior of gases enclosed in a chamber and formulated the gas law named for him. He also contributed to physiology and to the founding of modern chemistry. Another important factor in the scientific revolution was the rise of learned societies and academies in various countries. The earliest of these were in Italy and Germany, and were short-lived. More influential were the Royal Society of England, 1660, and the Academy of Sciences in France, 1666. The former was a private institution in London, and included such scientists as John Wallis, William Brouncker, Thomas Sydenham, John Mayo, and Christopher Wren, who contributed not only to architecture, but also to astronomy and anatomy. The latter, in Paris, was a government institution, and included, as a foreign member, the Dutchman Huygens. In the 18th century, important royal academies were established at Berlin, 1700, and at St. Petersburg, 1724. The societies and academies provided the principal opportunities for the publication and discussion of scientific results during and after the scientific revolution. In 1690, James Bernoulli showed that the cycloid is the solution to the Dodecahron problem. In 1691, Johann Bernoulli showed that a chain freely suspended from 2 points will form a catenary. In 1691, James Bernoulli showed that the catenary curve has the lowest center of gravity that any chain hung from 2 fixed points can have. In 1696, Johann Bernoulli showed that the cycloid is the solution to the Brachis-Dodecahron problem. Early thermodynamics. A precursor of the engine was designed by the German scientist Otto von Guericke, who, in 1650, designed and built the world's first vacuum pump, and created the world's first ever vacuum known as the Magdeburg Hemispheres experiment. He was driven to make a vacuum to disprove Aristotle's long-held supposition that nature abhors a vacuum. Shortly thereafter, Irish physicist and chemist Boyle had learned of Guericke's designs, and in 1656, in coordination with English scientist Robert Hooke, built an air pump. Using this pump, Boyle and Hooke noticed a pressure-volume correlation for a gas, PV equals K, where P is pressure, V is volume and K is a constant. This relationship is known as Boyle's law. In that time, air was assumed to be a system of motionless particles, and not interpreted as a system of moving molecules. The concept of thermal motion came 2 centuries later. Therefore Boyle's publication in 1660 speaks about a mechanical concept, the air spring. Later, after the invention of the thermometer, the property temperature could be quantified. This tool gave Gay-Lussac the opportunity to derive his law, which led shortly later to the ideal gas law. But, already before the establishment of the ideal gas law, an associate of Boyle's named Denis Papin built in 1679 a bone digester, which is a closed vessel with a tightly fitting lid that confines steam until a high pressure is generated. Later designs implemented a steam release valve to keep the machine from exploding. By watching the valve rhythmically move up and down, Papin conceived of the idea of a piston and cylinder engine. He did not, however, follow through with his design. Nevertheless, in 1697, based on Papin's designs, engineer Thomas Savery built the first engine. Although these early engines were crude and inefficient, they attracted the attention of the leading scientists of the time. Hence, prior to 1698 and the invention of the Savery engine, Horses were used to power pulleys, attached to buckets, which lifted water out of flooded salt mines in England. In the years to follow, more variations of steam engines were built, such as the Newcomen engine, and later the Watt engine. In time, these early engines would eventually be utilized in place of horses. Thus, each engine began to be associated with a certain amount of horsepower depending upon how many horses it had replaced. The main problem with these first engines was that they were slow and clumsy, converting less than 2% of the input fuel into useful work. In other words, large quantities of coal or wood had to be burned to yield only a small fraction of work output. Hence the need for a new science of engine dynamics was born. 18th century developments. During the 18th century, the mechanics founded by Newton was developed by several scientists as more mathematicians learned calculus and elaborated upon its initial formulation. The application of mathematical analysis to problems of motion was known as rational mechanics, or mixed mathematics, and was later termed classical mechanics. Mechanics. Daniel Bernoulli, 1700–1782. In 1714, Brooke-Taylor derived the fundamental frequency of a stretched vibrating string in terms of its tension and mass per unit length by solving a differential equation. The Swiss mathematician Daniel Bernoulli, 1700–1782, made important mathematical studies of the behavior of gases, anticipating the kinetic theory of gases developed more than a century later, and has been referred to as the first mathematical physicist. In 1733, Daniel Bernoulli derived the fundamental frequency and harmonics of a hanging chain by solving a differential equation. In 1734, Bernoulli solved the differential equation for the vibrations of an elastic bar clamped at one end. Bernoulli's treatment of fluid dynamics and his examination of fluid flow was introduced in his 1738 work Hydrodynamica. Rational mechanics dealt primarily with the development of elaborate mathematical treatments of observed motions, using Newtonian principles as a basis, and emphasized improving the tractability of complex calculations and developing of legitimate means of analytical approximation. A representative contemporary textbook was published by Johann Baptist Horvath. By the end of the century, analytical treatments were rigorous enough to verify the stability of the solar system solely on the basis of Newton's laws without reference to divine intervention, even as deterministic treatments of systems as simple as the three-body problem in gravitation remained intractable. In 1705, Edmund Halley predicted the periodicity of Halley's comet. William Herschel discovered Uranus in 1781, and Henry Cavendish measured the gravitational constant and determined the mass of the Earth in 1798. In 1783, John Michell suggested that some objects might be so massive that not even light could escape from them. In 1739, Leonhard Euler solved the ordinary differential equation for a forced harmonic oscillator and noticed the resonance phenomenon. In 1742, Colin Maclaurin discovered his uniformly rotating self-gravitating spheroids. British work carried on by mathematicians such as Taylor and Maclaurin fell behind continental developments as the century progressed. Meanwhile, work flourished at scientific academies on the continent, led by such mathematicians as Bernoulli, Euler, Lagrange, Laplace, and Legendre. In 1743, Jean-Léon d'Alembert published his Traité de dynamique, in which he introduces the concept of generalized forces for accelerating systems and systems with constraints. In 1747, Pierre-Louis Maupertuis applied minimum principles to mechanics. In 1759, Euler solved the partial differential equation for the vibration of a rectangular drum. In 1764, Euler examined the partial differential equation for the vibration of a circular drum, and found one of the Bessel function solutions. In 1776, John Smeaton published a paper on experiments relating power, work, momentum, and kinetic energy, and supporting the conservation of energy. In 1788, Joseph Louis Lagrange presented Lagrange's equations of motion in mécanique analytique. In 1789, Antoine Lavoisier states the law of conservation of mass. Newton's mechanics received brilliant exposition in both Lagrange's 1788 work and the celestial mechanics, 1799-1825, of Pierre-Simon Laplace. Thermodynamics. During the 18th century, thermodynamics was developed through the theories of weightless imponderable fluids such as heat, caloric electricity, and phlogiston, which was rapidly overthrown as a concept following Lavoisier's identification of oxygen gas late in the century. Assuming that these concepts were real fluids, their flow could be traced through a mechanical apparatus or chemical reactions. This tradition of experimentation led to the development of new kinds of experimental apparatus, such as the Leyden jar, and new kinds of measuring instruments, such as the calorimeter, and improved versions of old ones, such as the thermometer. Experiments also produced new concepts, such as the University of Glasgow experimenter Joseph Black's notion of latent heat and Philadelphia intellectual Benjamin Franklin's characterization of electrical fluid as flowing between places of excess and deficit, a concept later reinterpreted in terms of positive and negative charges. Franklin also showed that lightning is electricity in 1752. The accepted theory of heat in the 18th century viewed it as a kind of fluid, called caloric, although this theory was later shown to be erroneous. A number of scientists adhering to it nevertheless made important discoveries useful in developing the modern theory, including Joseph Black, 1728-99, and Henry Cavendish, 1731-1810. Opposed to this caloric theory, which had been developed mainly by the chemists, was the less accepted theory dating from Newton's time that heat is due to the motions of the particles of a substance. This mechanical theory gained support in 1798 from the cannon boring experiments of Count Rumford. Benjamin Thomson, who found a direct relationship between heat and mechanical energy. While it was recognized early in the 18th century that finding absolute theories of electrostatic and magnetic force akin to Newton's principles of motion would be an important achievement, none were forthcoming. This impossibility only slowly disappeared as experimental practice became more widespread and more refined in the early years of the 19th century in places such as the newly established Royal Institution in London. Meanwhile, the analytical methods of rational mechanics began to be applied to experimental phenomena, most influentially with the French mathematician Joseph Fourier's analytical treatment of the flow of heat, as published in 1822. Joseph Priestley proposed an electrical inverse square law in 1767, and Charles Augustin de Coulomb introduced the inverse square law of electrostatics in 1798. At the end of the century, the members of the French Academy of Sciences had attained clear dominance in the field. At the same time, the experimental tradition established by Galileo and his followers persisted. The Royal Society and the French Academy of Sciences were major centers for the performance and reporting of experimental work. Experiments in mechanics, optics, magnetism, static electricity, chemistry, and physiology were not clearly distinguished from each other during the 18th century, but significant differences in explanatory schemes and, thus, experiment design were emerging. Chemical experimenters, for instance, defied attempts to enforce a scheme of abstract Newtonian forces onto chemical affiliations, and instead focused on the isolation and classification of chemical substances and reactions. 19th century. British physicist Michael Faraday, 1791-1867. In 1800, Alessandro Volta invented the electric battery, known as the voltaic pile, and thus improved the way electric currents could also be studied. A year later, Thomas Young demonstrated the wave nature of light, which received strong experimental support from the work of Augustin Jean Fresnel, and the principle of interference. In 1813, Peter Ewart supported the idea of the conservation of energy in his paper on the measure of moving force. In 1820, Hans Christian Ørsted found that a current-carrying conductor gives rise to a magnetic force surrounding it, and within a week after Ørsted discovery reached France, André-Marie Ampère discovered that two parallel electric currents will exert forces on each other. In 1821, William Hamilton began his analysis of Hamilton's characteristic function. In 1821, Michael Faraday built an electricity-powered motor, while George Ohm stated his law of electrical resistance in 1826, expressing the relationship between voltage, current, and resistance in an electric circuit. A year later, botanist Robert Brown discovered Brownian motion, pollen grains in water undergoing movement resulting from their bombardment by the fast-moving atoms or molecules in the liquid. In 1831, Faraday, and independently Joseph Henry, discovered the reverse effect, the production of an electric potential or current through magnetism known as electromagnetic induction. These two discoveries are the basis of the electric motor and the electric generator, respectively. In 1834, Carl Jacobi discovered his uniformly rotating self-gravitating ellipsoids. In 1834, John Russell observed a non-decaying solitary water wave, soliton, in the Union Canal near Edinburgh, and used a water tank to study the dependence of solitary water wave velocities on wave amplitude and water depth. In 1835, William Hamilton stated Hamilton's canonical equations of motion. In the same year, Gaspard Coriolis examined theoretically the mechanical efficiency of water wheels and deduced the Coriolis effect. In 1841, Julius Robert von Mayer, an amateur scientist, wrote a paper on the conservation of energy, but his lack of academic training led to its rejection. In 1842, Christian Doppler proposed the Doppler effect. In 1847, Hermann von Helmholtz formally stated the law of conservation of energy. In 1851, Leon Foucault showed the Earth's rotation with a huge pendulum, Foucault pendulum. There were important advances in continuum mechanics in the first half of the century, namely formulation of laws of elasticity for solids and discovery of Navier-Stokes equations for fluids. Laws of thermodynamics. William Thomson, 1824–1907, later Lord Kelvin. In the 19th century, the connection between heat and mechanical energy was established quantitatively by Julius Robert von Mayer and James Prescott Joule, who measured the mechanical equivalent of heat in the 1840s and 1849. Joule published results from his series of experiments, including the paddle wheel experiment, which showed that heat is a form of energy, a fact that was accepted in the 1850s. The relation between heat and energy was important for the development of steam engines. And in 1824 the experimental and theoretical work of Sadi Carnot was published. Carnot captured some of the ideas of thermodynamics in his discussion of the efficiency of an idealized engine. Sadi Carnot's work provided a basis for the formulation of the first law of thermodynamics, a restatement of the law of conservation of energy which was stated around 1850 by William Thomson, later known as Lord Kelvin, and Rudolf Clausius. Lord Kelvin, who had extended the concept of absolute zero from gases to all substances in 1848, drew upon the engineering theory of Lazare Carnot, Sadi Carnot, and Émile Clapeyron, as well as the experimentation of James Prescott Joule on the interchangeability of mechanical, chemical, thermal, and electrical forms of work to formulate the first law. Kelvin and Clausius also stated the second law of thermodynamics, which was originally formulated in terms of the fact that heat does not spontaneously flow from a colder body to a hotter. Other formulations followed quickly. For example, the second law was expounded in Thomson and Peter Guthrie Tait's influential work Treatise on Natural Philosophy, and Kelvin, in particular, understood some of the law's general implications. The second law was the idea that gases consist of molecules in motion had been discussed in some detail by Daniel Bernoulli in 1738, but had fallen out of favor, and was revived by Clausius in 1857. In 1850, Hippolyte Fizeau and Leon Foucault measured the speed of light in water, and find that it is slower than in air, in support of the wave model of light. In 1852, Joule and Thomson demonstrated that a rapidly expanding gas cools, later named the Joule-Thomson effect or Joule-Kelvin effect. Hermann von Helmholtz puts forward the idea of the heat death of the universe in 1854, the same year that Clausius established the importance of dq/t, Clausius's theorem, though he did not yet name the quantity. James Clerk Maxwell. James Clerk Maxwell, 1831-1879. In 1859, James Clerk Maxwell discovered the distribution law of molecular velocities. Maxwell showed that electric and magnetic fields are propagated outward from their source at a speed equal to that of light, and that light is one of several kinds of electromagnetic radiation, differing only in frequency and wavelength from the others. In 1859, Maxwell worked out the mathematics of the distribution of velocities of the molecules of a gas. The wave theory of light was widely accepted by the time of Maxwell's work on the electromagnetic field, and afterward the study of light and that of electricity and magnetism were closely related. In 1864, James Maxwell published his papers on a dynamical theory of the electromagnetic field, and stated that light is an electromagnetic phenomenon, in the 1873 publication of Maxwell's Treatise on Electricity and Magnetism. This work drew upon theoretical work by German theoreticians such as Carl Friedrich Gauss and Wilhelm Weber. The encapsulation of heat in particulate motion, and the addition of electromagnetic forces to Newtonian dynamics established an enormously robust theoretical underpinning to physical observations. The prediction that light represented a transmission of energy in wave form through a luminiferous ether, and the seeming confirmation of that prediction with Helmholtz student Heinrich Hertz's 1888 detection of electromagnetic radiation, was a major triumph for physical theory, and raised the possibility that even more fundamental theories based on the field could soon be developed. Experimental confirmation of Maxwell's theory was provided by Hertz, who generated and detected electric waves in 1886 and verified their properties, at the same time foreshadowing their application in radio, television, and other devices. In 1887, Heinrich Hertz discovered the photoelectric effect. Research on the transmission of electromagnetic waves began soon after, with many scientists and inventors conducting experiments during the 1890s, leading to the first successful commercial wireless telegraphy system developed by Guglielmo Marconi. At the end of that decade, see invention of radio. The atomic theory of matter had been proposed again in the early 19th century by the chemist John Dalton, and became one of the hypotheses of the kinetic molecular theory of gases developed by Clausius and James Clerk Maxwell to explain the laws of thermodynamics. The kinetic theory in turn led to the statistical mechanics of Ludwig Boltzmann, 1844-1906, and Josiah Willard Gibbs, 1839-1903, which held that energy, including heat, was a measure of the speed of particles. Interrelating the statistical likelihood of certain states of organization of these particles with the energy of those states, Clausius reinterpreted the dissipation of energy to be the statistical tendency of molecular configurations to pass toward increasingly likely, increasingly disorganized states, coining the term entropy to describe the disorganization of a state. The statistical versus absolute interpretations of the Second Law of Thermodynamics set up a dispute that would last for several decades, producing arguments such as Maxwell's demon, and that would not be held to be definitively resolved until the behavior of atoms was firmly established in the early 20th century. In 1902, James Jeans found the length scale required for gravitational perturbations to grow in a static nearly homogeneous medium. Marie Skłodowska-Curie, 1867-1934. At the end of the 19th century, physics had evolved to the point at which classical mechanics could cope with highly complex problems involving macroscopic situations. Thermodynamics and kinetic theory were well established. Geometrical and physical optics could be understood in terms of electromagnetic waves, and the conservation laws for energy and momentum and mass were widely accepted. So profound were these and other developments, that it was generally accepted that all the important laws of physics had been discovered, and that, henceforth, research would be concerned with clearing up minor problems, and particularly with improvements of method and measurement. However, around 1900 serious doubts arose about the completeness of the classical theories. The triumph of Maxwell's theories, for example, was undermined by inadequacies that had already begun to appear and their inability to explain certain physical phenomena, such as the energy distribution in black-body radiation and the photoelectric effect, while some of the theoretical formulations led to paradoxes when pushed to the limit. Prominent physicists such as Hendrik Lorentz, Emil Cohn, Ernst Mach, and Wilhelm Wien believed that some modification of Maxwell's equations might provide the basis for all physical laws. These shortcomings of classical physics were never to be resolved, and new ideas were required. At the beginning of the 20th century, a major revolution shook the world of physics, which led to a new era, generally referred to as modern physics. Radiation experiments. J. Thomson, 1856–1940, was a British physicist who discovered electrons and isotopes, and invented the mass spectrometer. Thomson was awarded the 1906 Nobel Prize in Physics. In the 19th century, experimenters began to detect unexpected forms of radiation. Wilhelm Röntgen caused a sensation with his discovery of X-rays in 1895. In 1896, Henri Becquerel discovered that certain kinds of matter emit radiation on their own accord. In 1897, J. Thomson discovered the electron, and new radioactive elements found by Marie and Pierre Curie raised questions about the supposedly indestructible atom and the nature of matter. Marie and Pierre coined the term radioactivity to describe this property of matter, and isolated the radioactive elements radium and polonium. Ernest Rutherford and Frederick Soddy identified two of Becquerel's forms of radiation with electrons and the element helium. Rutherford identified and named two types of radioactivity, and in 1911 interpreted experimental evidence as showing that the atom consists of a dense, positively charged nucleus surrounded by negatively charged electrons. Classical theory, however, predicted that this structure should be unstable. Classical theory had also failed to explain successfully two other experimental results that appeared in the late 19th century. One of these was the demonstration by Albert A. Michelson and Edward W. Morley, known as the Michelson-Morley experiment, which showed there did not seem to be a preferred frame of reference at rest with respect to the hypothetical luminiferous ether for describing electromagnetic phenomena. Studies of radiation and radioactive decay continued to be a preeminent focus for physical and chemical research through the 1930s, when the discovery of nuclear fission opened the way to the practical exploitation of what came to be called atomic energy. Albert Einstein's theory of relativity. In 1905, a young 26-year-old German physicist, then a Bern patent clerk, named Albert Einstein, 1879–1955, showed how measurements of time and space are affected by motion between an observer and what is being observed. To say that Einstein's radical theory of relativity revolutionized science is no exaggeration. Although Einstein made many other important contributions to science, the theory of relativity alone represents one of the greatest intellectual achievements of all time. Although the concept of relativity was not introduced by Einstein, his major contribution was the recognition that the speed of light in a vacuum is constant, and an absolute physical boundary for motion. This does not have a major impact on a person's day-to-day life, since we travel at speeds much slower than light speed. For objects traveling near light speed, however, the theory of relativity states that objects will move slower and shorten in length from the point of view of an observer on Earth. Einstein also derived the famous equation, E=mc², which reveals the equivalence of mass and energy. Special relativity. Albert Einstein, 1879–1955, who proposed that gravitation was a result of the presence of mass causing a curvature of space-time, which dictates a path that all freely moving objects must follow. Further information, History of Special Relativity. Einstein argued that the speed of light was a constant in all inertial reference frames, and that electromagnetic laws should remain valid independent of reference frame assertions, which rendered the ether superfluous to physical theory, and that held that observations of time and length varied relative to how the observer was moving with respect to the object being measured, what came to be called the special theory of relativity. It also followed that mass and energy were interchangeable quantities according to the equation E equals mc2. In another paper published the same year, Einstein asserted that electromagnetic radiation was transmitted in discrete quantities, quanta, according to a constant that the theoretical physicist Max Planck had posited in 1900 to arrive at an accurate theory for the distribution of blackbody radiation, an assumption that explained the strange properties of the photoelectric effect. The special theory of relativity is a formulation of the relationship between physical observations and the concepts of space and time. The theory arose out of contradictions between electromagnetism and Newtonian mechanics, and had great impact on both those areas. The original historical issue was whether it was meaningful to discuss the electromagnetic wave carrying ether and motion relative to it, and also whether one could detect such motion, as was unsuccessfully attempted in the Michelson-Morley experiment. Einstein demolished these questions and the ether concept in his special theory of relativity. However, his basic formulation does not involve detailed electromagnetic theory. It arises out of the question, what is time? Newton, in the Principia, 1686, had given an unambiguous answer, absolute, true, and mathematical time, of itself, and from its own nature, flows equably without relation to anything external, and by another name is called duration. This definition is basic to all classical physics. Einstein had the genius to question it, and found that it was incorrect. Instead, each observer necessarily makes use of their own scale of time. Furthermore, for two observers in relative motion, their time scales will differ. This induces a related effect on distance. Both space and time become relative concepts, fundamentally dependent on the observer. Each observer generates their own space-time framework, or coordinate system. All observers have equal validity, there being no absolute frame of reference. Motion is relative, but only relative to other observers. What is absolute is stated in Einstein's first relativity postulate. The basic laws of physics are identical for two observers who have a constant relative velocity with respect to each other. The special relativity made a profound effect on physics, started as a rethinking of the theory of electromagnetism. It found a new symmetry law of nature, now called Poincare symmetry, that replaced the old Galilean, see above, symmetry. Another long-lasting effect the special relativity exerted on dynamics. Although at the time it was credited as unification of mass and energy, now it is evident that relativistic dynamics established indeed a firm distinction between the res mass, that is an intrinsic property of a particle, and energy together with momentum, that are conserving quantities. The term mass in particle physics underwent a semantic change since late 20th century denotes the rest, or invariant, mass almost exclusively, that has little to do with masses of complex physical bodies. See mass in special relativity for the full story. General relativity. In 1916 Einstein was able to generalize this further, to deal with all states of motion including non-uniform acceleration, which became the general theory of relativity. In this theory Einstein also specified a new concept, the curvature of space-time, which described the gravitational effect at every point in space. In fact, the curvature of space-time completely replaced Newton's universal law of gravitation. According to Einstein, there was no such thing as a gravitational force. Rather, the presence of a mass causes a curvature of space-time in the vicinity of the mass, and this curvature dictates the space-time path that all freely moving objects must follow. It was also predicted from this theory that light should be subject to gravity, all of which was verified experimentally. This aspect of relativity explained the phenomena of light bending around the sun, predicted black holes as well as the cosmic microwave background radiation, a discovery rendering fundamental anomalies in the classic steady-state hypothesis. For his work on relativity, the photoelectric effect and black-body radiation, Einstein received the Nobel Prize in 1921. The gradual acceptance of Einstein's theories of relativity and the quantized nature of light transmission, and of Niels Bohr's model of the atom, created as many problems as they solved, leading to a full-scale effort to re-establish physics on new fundamental principles. Expanding relativity to cases of accelerating reference frames, the general theory of relativity. In the 1910s, Einstein posited an equivalence between the inertial force of acceleration and the force of gravity, leading to the conclusion that space is curved and finite in size, and the prediction of such phenomena as gravitational lensing and the distortion of time and gravitational fields. Quantum mechanics. Max Planck, 1858-1947. Although relativity resolved the electromagnetic phenomena conflict demonstrated by Michelson and Morley, a second theoretical problem was the explanation of the distribution of electromagnetic radiation emitted by a black body. Experiments showed that at shorter wavelengths, toward the ultraviolet end of the spectrum, the energy approached zero, but classical theory predicted it should become infinite. The squaring discrepancy, known as the ultraviolet catastrophe, was solved by the new theory of quantum mechanics. Quantum mechanics is the theory of atoms and subatomic systems. Approximately the first 30 years of the 20th century represent the time of the conception and evolution of the theory. The basic ideas of quantum theory were introduced in 1900 by Max Planck, 1858-1947, who was awarded the Nobel Prize for Physics in 1918 for his discovery of the quantified nature of energy. The quantum theory, which previously relied on the correspondence at large scales between the quantized world of the atom and the continuities of the classical world, was accepted when the Compton effect established that light carries momentum and can scatter off particles, and when Louis de Broglie asserted that matter can be seen as behaving as a wave in much the same way as electromagnetic waves behave like particles, wave-particle duality. Werner Heisenberg, 1901-1976. In 1905, Einstein used the quantum theory to explain the photoelectric effect, and in 1913 the Danish physicist Niels Bohr used the same constant to explain the stability of Rutherford's atom as well as the frequencies of light emitted by hydrogen gas. The quantized theory of the atom gave way to a full-scale quantum mechanics. In the 1920s, new principles of a quantum rather than a classical mechanics, formulated in matrix form by Werner Heisenberg, Max Born, and Pascual Jordan in 1925, were based on the probabilistic relationship between discrete states and denied the possibility of causality. Quantum mechanics was extensively developed by Heisenberg, Wolfgang Pauli, Paul Dirac, and Erwin Schrödinger, who established an equivalent theory based on waves in 1926, but Heisenberg's 1927 uncertainty principle, indicating the impossibility of precisely and simultaneously measuring position and momentum, and the Copenhagen interpretation of quantum mechanics, named after Bohr's home city, continued to deny the possibility of fundamental causality, though opponents such as Einstein would metaphorically assert that God does not play dice with the universe. The new quantum mechanics became an indispensable tool in the investigation and explanation of phenomena at the atomic level. Also in the 1920s, Satyendranath Bose's work on photons and quantum mechanics provided the foundation for Bose-Einstein statistics, the theory of the Bose-Einstein condensate. The spin statistics theorem established that, in quantum mechanics, any particle may be either a boson, that means its statistics is Bose-Einstein, or a fermion, that means its statistics is Fermi-Dirac. It was later found that all fundamental bosons transmit forces, like the photon that transmits light. Fermions are particles, like electrons and nucleons, and generally comprise the matter. Fermi-Dirac statistics later found numerous applications from astrophysics, see degenerate matter, to semiconductors. Contemporary and particle physics. Quantum field theory. In this Feynman diagram, an electron and a positron annihilate, producing a photon, represented by the blue sine wave, that becomes a quark-antiquark pair. Then one radiates a gluon, represented by the green spiral. As the philosophically inclined continued to debate the fundamental nature of the universe, quantum theories continued to be produced, beginning with Paul-Dirac's formulation of a relativistic quantum theory in 1928. However, attempts to quantize electromagnetic theory entirely were stymied throughout the 1930s by theoretical formulations yielding infinite energies. The situation was not considered adequately resolved until after World War II ended, when Julian Schwinger, Richard Feynman, and Sunehiro Tomonaga independently posited the technique of renormalization, which allowed for an establishment of a robust quantum electrodynamics, QED. Meanwhile, new theories of fundamental particles proliferated with the rise of the idea of the quantization of fields through exchange forces regulated by an exchange of short-lived virtual particles, which were allowed to exist according to the laws governing the uncertainties inherent in the quantum world. Notably, Hideki Yukawa proposed that the positive charges of the nucleus were kept together courtesy of a powerful but short-range force mediated by a particle intermediate in mass between the size of an electron and a proton. This particle, called the pion, was identified in 1947, but it was part of a slew of particle discoveries beginning with the neutron, the positron, a positively charged antimatter version of the electron, and the muon, a heavier relative to the electron, in the 1930s, and continuing after the war with a wide variety of other particles detected in various kinds of apparatus, cloud chambers, nuclear emulsions, bubble chambers, and coincidence counters. At first these particles were found primarily by the ionized trails left by cosmic rays, but were increasingly produced in newer and more powerful particle accelerators. Outside of particle physics, significant advances of the time were invention of lasers, Nobel Prize in Physics, of 1964. Experimental and theoretical researches of superconductivity, especially invention of a quantum theory of superconductivity by Vitaly Ginzburg and Lev Landau, Nobel Prize, of 2002, and, later, its explanation with Cooper pairs, also a Nobel Prize. The Cooper pair was one of early examples of a quasi-particle. Unified field theories. Einstein deemed that all fundamental interactions in nature can be explained in a single theory. Unified field theories were numerous attempts to merge several interactions. One of formulations of such theories, as well as field theories in general, is a gauge theory, a generalization of the idea of symmetry. Eventually the Standard Model, see below, succeeded in unification of strong, weak, and electromagnetic interactions. All attempts to unify gravitation with something else failed. This section requires expansion. January 2014. Standard Model. The Standard Model. The interaction of these particles by scattering and decay provided a key to new fundamental quantum theories. Marie-Gell-Mann and Yuval-Ne'eman brought some order to these new particles by classifying them according to certain qualities, beginning with what Gell-Mann referred to as the Eightfold Way. While its further development, the quark model, at first seemed inadequate to describe strong nuclear forces, allowing the temporary rise of competing theories such as the S-matrix, the establishment of quantum chromodynamics. In the 1970s finalized a set of fundamental and exchange particles, which allowed for the establishment of a standard model based on the mathematics of gauge invariance, which successfully described all forces except for gravitation, and which remains generally accepted within its domain of application. The Standard Model groups the electroweak interaction theory and quantum chromodynamics into a structure denoted by the gauge group SU3, SU2, U1. The formulation of the unification of the electromagnetic and weak interactions in the Standard Model is due to Abdus-Salam, Stephen Weinberg, and, subsequently, Sheldon Glashow. Electroweak theory was later confirmed experimentally by observation of neutral weak currents and distinguished by the 1979 Nobel Prize in Physics. Since the 1970s, fundamental particle physics has provided insights into early universe cosmology, particularly the Big Bang theory proposed as a consequence of Einstein's general theory of relativity. However, starting from the 1990s, astronomical observations have also provided new challenges, such as the need for new explanations of galactic stability, the problem of dark matter, and accelerating expansion of the universe, the problem of dark energy. While accelerators have confirmed most aspects of the Standard Model by detecting expected particle interactions at various collision energies, no theory reconciling general relativity with the Standard Model has yet been found, although supersymmetry and string theory were believed by many theorists to be a promising avenue forward. The Large Hadron Collider, however, which began operating in 2008, has failed to find any evidence whatsoever that is supportive of supersymmetry and string theory. Cosmology. Cosmology may be said to have become a serious research question with the publication of Einstein's general theory of relativity, 1916, although it did not enter the scientific mainstream until a period known as the Golden Age of General Relativity. About a decade later, in the midst of the great debates, Hubble and Slipher discovered the expansion of universe in the 1920s, measuring the redshifts of Doppler spectra from galactic nebulae. Using Einstein's general relativity, Lemaitre and Gamow formulated what would become known as the Big Bang theory. A rival, called the steady-state theory, was devised by Hoyle, Gold, Narlik R., and Bondi. Cosmic background radiation was verified in the 1960s by Penzias and Wilson, and this discovery favored the Big Bang at the expense of the steady-state scenario. Later work was by Smoot et al., 1989, among other contributors, using data from the Cosmic Background Explorer, COBE, and the Wilkinson Microwave Anisotropy Probe, WMAP, satellites, that refined these observations. The 1980s, the same decade of the COBE measurements, also saw the proposal of inflation theory by Guth. Recently, the problems of dark matter and dark energy have risen to the top of the cosmology agenda. Higgs boson. One possible signature of a Higgs boson from a simulated proton-proton collision. It decays almost immediately into two jets of hadrons and two electrons, visible as lines. On July 4, 2012, physicists working at CERN's Large Hadron Collider announced that they had discovered a new subatomic particle greatly resembling the Higgs boson, a potential key to an understanding of why elementary particles have mass, and indeed to the existence of diversity and life in the universe. For now, some physicists are calling it a Higgs-like particle. Joan Candela, of the University of California, Santa Barbara, said, "It's something that may, in the end, be one of the biggest observations of any new phenomenon in our field in the last 30 or 40 years, going way back to the discovery of quarks, for example." Michael Turner, a cosmologist at the University of Chicago, and the chairman of the Physics Center Board, said, "This is a big moment for particle physics. And a crossroads. Will this be the high water mark, or will it be the first of many discoveries that point us toward solving the really big questions that we have posed?" Dr. Peter Higgs was one of 6 physicists, working in 3 independent groups, who in 1964 invented the notion of the cosmic molasses, or Higgs field. The others were Tom Kibble of Imperial College, London, Carl Hagen, of the University of Rochester, Gerald Guralnick of Brown University, and François Englert and Robert Brout, both of Universiteit Libre de Bruxelles. Although they have never been seen, Higgs-like fields play an important role in theories of the universe and in string theory. Under certain conditions, according to the strange accounting of Einsteinian physics, they can become suffused with energy that exerts an anti-gravitational force. Such fields have been proposed as the source of an enormous burst of expansion, known as inflation, early in the universe, and, possibly, as the secret of the dark energy that now seems to be speeding up the expansion of the universe. The physical sciences. With increased accessibility to and elaboration upon advanced analytical techniques, in the 19th century, physics was defined as much, if not more, by those techniques than by the search for universal principles of motion and energy and the fundamental nature of matter. Fields such as acoustics, geophysics, astrophysics, aerodynamics, plasma physics, low-temperature physics, and solid-state physics joined optics, fluid dynamics, electromagnetism, and mechanics as areas of physical research. In the 20th century, physics also became closely allied with such fields as electrical, aerospace, and materials engineering. And physicists began to work in government and industrial laboratories as much as in academic settings. Following World War II, the population of physicists increased dramatically and came to be centered on the United States, while, in more recent decades, physics has become a more international pursuit than at any time in its previous history. Timeline of important physics publications. Name living time contribution Aristotle 384-322 BCE Physikeos Kodations Archimedes 287-212 BCE On floating bodies Ptolemy 90-168 Almagest, Geographia. Apostoles Carolus in 965-1040 Book of Optics Copernicus 1473-1543 On the Revolutions of the Celestial Spheres 1543, Galilei 1564-1642 Dialogue concerning the two chief world systems 1632, Descartes 1596-1650 Meditations on First Philosophy 1641, Newton 1643-1727 Philosophia Naturalis Principia Mathematica 1687, Faraday 1791-1867 Experimental Researches in Electricity, Vols. I. 1839, 1844, Maxwell 1831-1879 A Treatise on Electricity and Magnetism, 1873, Einstein 1879-1955 Omnus Mirabilis Papers, 1905. Influential physicists. This list of famous or notable persons has no clear inclusion or exclusion criteria. Please help to define clear inclusion criteria, and edit the list to contain only subjects that fit those criteria. January 2014. The following is a gallery of highly influential and important figures in the history of physics. For a list that includes even more people, see List of physicists. Archimedes, c. 287-c. 212 BCE, described buoyancy, developed formulae for the areas and volumes of spheres, cylinders, parabolas, worked extensively with levers, invented the Archimedes screw, developed siege engines for warfare to impede the Roman invasion of Syracuse. Olazen, 965-1040, made significant improvements in optics, physical science, and the scientific method. In his Book of Optics, he showed through experiment that light travels in straight lines, and carried out various experiments with lenses, mirrors, refraction, and reflection, which earned him the title of the father of modern optics. Nicholas Copernicus, 1473-1543, published De Revolutionibus Orbium Celestium, on the revolutions of the celestial spheres, in 1543, often considered the starting point of modern astronomy, in which he argued that the Earth and the other planets revolved around the Sun, heliocentrism. Galileo Galilei, 1564-1642, discovered the uniform acceleration rate of falling bodies, improved on the refracting telescope, discovered the 4 largest moons of Jupiter, described projectile motion and the concept of weight, known for championing of the Copernican theory of heliocentrism against church opposition. Johannes Kepler, 1571–1630, used the accurate observations of Tycho Brahe to formulate three fundamental laws of planetary motion, described elliptical motion of planets around the Sun, developed early telescopes, invented the convex eyepiece, discovered the means of determining the magnifying power of lenses. Evangelista Torricelli, 1608–47, invented the barometer, a glass tube of mercury inverted into a dish, found that the change of height of the mercury each day was from atmospheric pressure, worked in geometry, and developed integral calculus, published findings on fluid and projectile motion in his 1644 Opera Geometrica, geometric works. Blaise Pascal, 1623–62, experimented with fluids, formulated Pascal's law in the 1650s stating that the pressure applied to a fluid taken in a closed container is transmitted with equal force throughout the container, proved that air has weight and that air pressure can produce a vacuum, namesake of the unit of pressure, the Pascal law. Christian Huygens, 1629–95. Studied the rings of Saturn and discovered its moon Titan, invented the pendulum clock, studied optics and centrifugal force, theorized that light consists of waves, Huygens' Fresnel principle, which became instrumental in the understanding of wave-particle duality. Robert Hooke, 1635–1703, formulated the law of elasticity, invented the balance spring, the spiral spring wheel in watches, the Gregorian telescope, and the first screw-divided quadrant. Constructed first arithmetical machine, improved cell theory with a microscope. Sir Isaac Newton, 1642–1727, established three laws of motion and a law of universal gravitation in his Philosophiae Naturalis Principia Mathematica, 1687, laid foundations for classical mechanics, built the first practical reflecting telescope, the Newtonian telescope, observed that a prism splits white light into the colors of the visible spectrum, formulated a law of cooling, co-invented calculus. Henry Cavendish, 1731–1810, greatest English chemist and physicist of his age, researched composition of the atmosphere, the properties of different gases, the synthesis of water, the law of electrical attraction and repulsion, a mechanical theory of heat, calculated the weight of the Earth in the Cavendish experiment, determined the universal gravitational constant. Charles Augustin de Coulomb, 1736–1806, formulated a law in 1785 which described the electrostatic interaction between electrically charged particles, attraction and repulsion, and was essential to the development of the theory of electromagnetism, namesake of the unit of electric charge, the coulomb. C. Alessandro Volta, 1745–1827, built the first electric battery, the voltaic pile. In the 19th century, did substantial work with electric currents, namesake of the unit of electric potential, the volt. V. Thomas Young, 1773–1829, established the principle of interference of light, resurrected the century-old theory that light is a wave, helped decipher the Rosetta's tone. Hans Christian Zero Ørsted, 1777–1851, discovered that electric currents create magnetic fields, an important aspect of electromagnetism, shaped advances in science in the late 19th century, namesake of the Ørsted. O, the CGS unit of magnetic H field strength. André-Marie Ampère, 1777–1836, main founder of electrodynamics, showed how an electric current produces a magnetic field, stated that the mutual action of two lengths of current-carrying wire is proportional to their lengths and to the intensities of their currents. Amperes Law, namesake of the unit of electric current, the ampere. Joseph von Fraunhofer, 1787–1826, first to study the dark lines of the sun's spectrum, now known as Fraunhofer lines, first to use extensively the diffraction grating, a device that disperses light more effectively than a prism does, set the stage for the development of spectroscopy, making optical glass and achromatic telescope objectives. George Ohm, 1789-1854, found that there is a direct proportionality between the electric current I and the potential difference, voltage, V applied across a conductor, and that this current is inversely proportional to the resistance R in the circuit, or I equals V/R, known as Ohm's law, namesake of the unit of electrical resistance, the ohm. Michael Faraday, 1791-1867, showed how a changing magnetic field can be used to generate an electric current. Faraday's law of induction applied this knowledge to the development of several electrical machines, described principles of electrolysis, early pioneer in the field of low-temperature study. Christian Doppler, 1800–353, first described how the observed frequency of light and sound waves is affected by the relative motion of the source and the detector, a phenomenon which became known as the Doppler effect. James Prescott Joule, 1800–1889, discovered that heat is a form of energy. Ideas led to the theory of conservation of energy, worked with Lord Kelvin to develop the absolute scale of temperature, made observations on magnetostriction, found the relationship between current through resistance and the heat dissipated, now called Joule's law. William Thomson, 1st Baron Kelvin, 1824–1907, major figure in the history of thermodynamics, helped develop law of conservation of energy, studied wave motion and vortex motion in hydrodynamics, and produced a dynamical theory of heat, formulated of the first and second laws of thermodynamics. James Clerk Maxwell, 1831–79, united electricity, magnetism, and optics into a consistent electromagnetic theory, formulated Maxwell's equations to show that electricity, magnetism, and light are manifestations of the electromagnetic field, developed the Maxwell-Boltzmann distribution, statistical means of describing aspects of the kinetic theory of gases. Ernst Mach, 1838–1916, contributed the Mach number, studied shock waves and how airflow is disturbed at the speed of sound, influenced logical positivism, forerunner of Einstein's relativity, through his criticism of Newton. Ludwig Boltzmann, 1844–1906, developed statistical mechanics, how the properties of atoms' mass, charge, and structure determine the visible properties of matter, such as viscosity, thermal conductivity, and diffusion, developed the kinetic theory of gases. Wilhelm Röntgen, 1845–1923, produced and detected electromagnetic radiation in a wavelength range of X-rays, or Röntgen rays, in 1895, for which he earned the first Nobel Prize in Physics, in 1901, namesake of element 111, Röntgenium. Henri Becquerel, 1852–1908, discovered radioactivity along with Marie Skłodowska-Curie and Pierre Curie, for which all three won the 1903 Nobel Prize in Physics. Hendrik Lorentz, 1853–1928, clarified electromagnetic theory of light, shared the 1902 Nobel Prize in Physics with Pieter Zeeman for the discovery and theoretical explanation of the Zeeman effect, developed concept of local time, derived the transformation equation subsequently used by Albert Einstein to describe space and time. J. Thomson, 1856–1940, showed in 1897 that cathode rays were composed of a previously unknown negatively charged particle, later named the electron, discovered isotopes, invented the mass spectrometer, awarded the 1906 Nobel Prize in Physics for the discovery of the electron, and for his work on the conduction of electricity in gases. Nikola Tesla, 1856–1943, contributed to alternating current, AC, engineering, developed an AC induction motor, invented the Tesla coil, Heinrich Hertz, 1857–1894, clarified and expanded Maxwell's electromagnetic theory of light, first to prove the existence of electromagnetic waves by engineering instruments to transmit and receive radio pulses. Max Planck, 1858–1947, founded quantum mechanics. In 1900, showed how the energy of a photon is directly proportional to its frequency, won him the 1918 Nobel Prize in Physics. He then used his quantum hypothesis to formulate Planck's law, thereby resolving the ultraviolet catastrophe. Pieter Zeeman, 1865–1943, shared the 1902 Nobel Prize in Physics with Hendrik Lorentz for discovering the Zeeman effect, splitting a spectral line into several components in the presence of a static magnetic field. Marie Curie, 1867–1934, discovered the existence of radioactivity with Henri Becquerel, and her husband Pierre Curie, awarded the Nobel Prize in Physics, 1903, and the Nobel Prize in Chemistry, 1911, found techniques for isolating radioactive isotopes, isolated plutonium and radium. Robert Andrews Millikan, 1868–1953, measured the charge on the electron, worked on the photoelectric effect, performed vital research pertaining to cosmic rays. Ernest Rutherford, 1871–1937, considered father of nuclear physics, showed how the atomic nucleus has a positive charge, first to change one element into another by an artificial nuclear reaction, differentiated and named alpha and beta radiation, awarded Nobel Prize for Chemistry in 1908. Lise Meitner, 1878–1968, worked on radioactivity and nuclear physics, gave the first theoretical explanation for nuclear fission, for which her colleague, chemist Otto Hahn, was awarded the Nobel Prize. She is often mentioned, with Ida Noddack, as one of the most glaring examples of women's scientific achievement overlooked by the Nobel Committee. Albert Einstein, 1879–1955, revolutionized physics due to his theories of special and general relativity, described Brownian motion, awarded the Nobel Prize in Physics in 1921 for his work on the photoelectric effect, formulated mass-energy equivalence formula E=mc², published more than 300 scientific papers and over 150 non-scientific works, considered the father of modern physics. Niels Bohr, 1885–1962, used quantum mechanical model, known as the Bohr model, of the atom, which theorized that electrons travel in discrete orbits around the nucleus, showed how electron energy levels are related to spectral lines, received the Nobel Prize in Physics in 1922. Erwin Schrödinger, 1887–1961, formulated the Schrödinger equation in 1926, describing how the quantum state of a physical system changes with time, awarded the Nobel Prize in Physics in 1933. 2 years later proposed the thought experiment known as Schrödinger's cat. James Chadwick, 1891–1974. James Chadwick's major work is the discovery of the neutron, for which received the Nobel Prize in Physics in 1935. He was one of the primary British scientists who worked in the Manhattan Project in the United States during World War II. He was knighted in 1945 for achievements in physics. Louis A. Broglie, 1892–1987, researched quantum theory, discovered the wave nature of electrons, awarded the 1929 Nobel Prize in Physics. Ideas on the wave-like behavior of particles used by Erwin Schrödinger in his formulation of wave mechanics. Georges Lemaitre, 1894–1966, first person to propose the theory of the expansion of the universe, first to derive what is now known as Hubble's law, made the first estimation of what is now called the Hubble constant, which he published in 1927, 2 years before Hubble's article, proposed the Big Bang theory of the origin of the universe. Wolfgang Pauli, 1900–1958, pioneers of quantum physics, received the Nobel Prize in Physics in 1945, nominated by Albert Einstein, formulated the Pauli exclusion principle involving spin theory, underpinning the structure of matter and the whole of chemistry, published the Pauli-Villers regularization, formulated the Pauli equation, coined the phrase, not even wrong. Werner Heisenberg, 1901-1976, developed method to express ideas of quantum mechanics in terms of matrices. In 1925, published his famous uncertainty principle. In 1927, awarded Nobel Prize in Physics. In 1932. Enrico Fermi, 1901-1954, developed first nuclear reactor, Chicago Pile 1, contributed to quantum theory, nuclear and particle physics, and statistical mechanics, awarded the 1938 Nobel Prize in Physics for his work on induced radioactivity. Paul Dirac, 1902-1984, made fundamental contributions to the early development of quantum mechanics and quantum electrodynamics, formulated the Dirac equation describing the behavior of fermions, predicted the existence of antimatter, shared the 1933 Nobel Prize in Physics with Erwin Schrödinger. John Bardeen, 1908-1991, awarded Nobel Prize in Physics in 1956, with William Shockley and Walter Brattain, for the invention of the transistor, and again in 1972, with Leon Cooper and John Robert Schrieffer, for a fundamental theory of conventional superconductivity known as the BCS theory. John Wheeler, 1911-2008, revived interest in general relativity in the United States after World War II, worked with Niels Bohr to explain principles of nuclear fission, tried to achieve Einstein's vision of a unified field theory, coined the terms black hole, quantum foam, wormhole, and the phrase it from bit. Richard Feynman, 1918-1988, developed the path integral formulation of quantum mechanics, the theory of quantum electrodynamics, and the physics of the superfluidity of supercooled liquid helium, awarded the Nobel Prize in Physics in 1965, with Julian Schwinger and Sunehiro Tomonaga, developed the Feynman diagram representing subatomic particle behavior. Gerardus de Hooft, 1946-present, a Dutch theoretical physicist and professor at Utrecht University, he shared the 1999 Nobel Prize in Physics with his thesis advisor Martinus J. G. Veldman for elucidating the quantum structure of electroweak interactions. His work on electroweak theory was crucial to Peter Higgs in the development of Higgs Boson theory. Peter Higgs, 1929-present, along with François Englert, Robert Brout, Gerald Guralnik, C.R. Hagen, and Tom Kibble, he developed the theory of Higgs field and Higgs boson, which together form the Higgs mechanism that explains how subatomic particles gain their mass. However, CERN have been cautious with the results, stating that new tests are needed to confirm the discovery. He received the Nobel Prize in Physics in 2013 for his work on the mentioned mechanism. Stephen Hawking, 1942-present, provided, with Roger Penrose, theorems of general relativity regarding the occurrence of gravitational singularities, black holes, and theoretically predicted that black holes should emit radiation, Hawking radiation.